Our second speaker today will be Professor Hyoyoung Lee from SKKU, South Korea. Professor Hyoyoung Lee completed his PhD at the Department of Chemistry, University of Mississippi, United States in 1997. And his postdoc research at North Carolina State University. He worked in one of the national laboratories, Electronics and Telecommunication Research Institute, before moving to the Department of Chemistry, SKKU, as a full professor. He successfully served as the director of the National Creative Research Initiative program for 9 years. Currently, he has served as an associate director of Center for Integrated Nanostructure Physics, Institute of Basic Science at SKKU. His research interest is chiral induction of the racemic mixture by the polarized light, 0D to 2D semiconductors, including holy, graphene, and graphene, graphene quantum dots, transition metal dicrystallites, including the blue titanium, and their applications for energy conversion, including water splitting, CO2 and nitrogen reduction reactions, catalysis, and energy storage. He has written more than 116 articles in top-tier journals. Today, he brings to us the talk about phase-selective disorder of two-phase mixed heterogeneous titanium for energy and sustainability. Now, welcome Professor Hyoyoung Lee. Please.
Okay. Thank you for a very nice, kind introduction. And also, I'd like to thanks to the organizing committee members, especially for Yapei Zhang, and also the paper, the nano micro layers. Okay, so I'd like to thanks before my talk. Okay, today I'd like to talking about phase selective disorder of two phase of like this, which is the the TiO2 having a two phase. Okay, especially for energy application and the possible sustainability in our world. Okay, this is my brief outlines, and I'm going to introduce three different topics related with this one. Okay, and also the motivation of our researches, and also the next, and then why we need low energy bandgap materials for a photocatalyst, especially for P25, which is the mixed, right? Mixed P25 TiO2, and okay, we are trying to having a new concept for preparation of black and blue TiO2 at the room temperature. That is what I'm our main focusing here today. And then some hybrid type of the application using a blue TiO2 and very short future plans. Okay, this is our motivation. So everybody knows that what is the photocatalytic materials, especially to be a photocatalytic materials has to have a semiconducting materials, right? So in the semiconducting materials, usually people are working on the inorganic semiconductors. Nowadays, people are working on also the organic semiconductors. Today, as you can see here, the transition metal oxide. This is there are several metal oxide materials here. In addition, also transition metal chalcogenides, right? So nowadays, many people working on those two areas. Here is that especially for the TiO2, right? So this one is commercially selling 5 million tons a year. Okay, so this is very unique. Why is this good? Because of this one is the very stable in our Earth, in the especially, okay, as a photocatalyst, this is one of the best material, right? So people has been working on numerous TiO2 works, okay? But that is the advantage, especially for okay, the low cost and the high chemical stability and environmentally friendly. But there are some disadvantages. So usually, the most disadvantage is the harvest visible light, which we can using it in our inside the building, right? So okay, those are okay, cons and the pros. So this is the okay milestones in the development of the TiO2. So as you know that TiO2 and the first application is mentioned about is that in nature back to about 50 years ago. So showing that this material, semiconductor material, using the UV, they can produce the hydrogenation, the water splitting from the water. So after that, there are big okay achievement which having a P25. In this time, they talking about just okay one phase. But in this time, after okay about how many years? Okay, about is it about 20 years later? Okay, they develop P25, which is the mixed one. The anatase phase 70% and rutile phase 30%. So that is the best material from until now on. So after that, okay, over 20 years later later again, so they find out okay black TiO2. So okay, I will show you. So after this, okay, what is the next okay thing, the creation. So as you can see, people are looking for black TiO2 because many working on the why is this black TiO2? Because people are using this visible light and infrared light, especially for visible light. So here is that just white TiO2 they can observe in the UV light because the band gap is about 3.1 here electron volt. So our focusing is the making of the okay visible light absorption, the black TiO2. So as you can see here, so there are okay the basic okay unit here, okay Ti and the oxygens. So the basically okay TiO2 means Ti okay O2, isn't it? So depending on the crystal form, okay, there are 3 different forms in our nature, usually rutile phase and the anatase phase. Okay. So as I mentioned in the historical milestones, over 50 years, people are working on making of the black TiO2. So here is that the conditions, right? So as you can see here, okay, over 600, okay, there is some conditions, okay, 200 Celsius degree, which is the lowest temperature, right? So this is the chemical review, a chemical society review paper. It's about 5 years ago. And then all of the report here is that, okay, high temperature, right? So this is the over 50 years issue to make black TiO2. Okay, this is one of the example. This is the science paper, right? The science paper showing that they are making a black TiO2 from the, okay, so when they make a black TiO2, what is the happen in the crystal form? The crystalline form, which is the white one, if you're making of the black and making the crystal form into this order form. Okay, so I will show you a little bit later. Okay, this is the condition, what they have done. Why they publish in the science? So at the moment, okay, making of the condition is a low temperature, 200 Celsius degree and 20 bar with hydrogen. So they starting with the anatase phase, TiO2, and they reporting this one is the mild condition, right? So, okay, our question, our challenge is that, is it possible to make black and blue TiO2 at room temperature, not the 200 Celsius degree, and 1 atmosphere, not the 20 bar, in solution process. So this is the first challenging to producing mass production. So for a mass production, we have to do it in solution process. Okay, so how can we achieve? This is the over half-century issues. So as you can see, first our thinking. Okay, I have a experience. Okay, so first our thinking is that, as you can see here, TiO2, if you break down this Ti oxygen bond, if you can break down this Ti oxygen bond at room temperature, that is the issue. So in my previous postdoc at the North Carolina State University, and also the PhD doing organic synthesis, I have experience with the Birch reduction reaction reagent. So what is the Birch reduction reagent? Is that if you have ammonia in sodium, okay, ammonia is a colorless solution, but if you're adding a sodium, giving a very deep blue solution. What does it mean, the deep blue solution? It means that when the sodium alkali earth metal is to give an electron to the ammonia solution, and then this one is becomes plus charged, and in solution making of a lot of electrons in the solution. So our idea is that if you're having a certain at the room temperature in the reagent have a lot of electrons, and then this electron can attack this Ti 4+1, making of 3+. Then has to be disconnected. So this is already I know that how do we need to make this Birch reduction? Is that the boiling point of ammonia is -33 Celsius degree. So okay, so which means that even though -30 Celsius degree, we can break down this bond. That is meant here. Okay, so which is I was looking for very strong reducing agent working with the room temperature processing. Okay, so this is our result. If you treat with the TiO2 in the solution, and then, okay, we adapted with the lithium in ethylene diamine. Ethylene diamine is the in solution solvent, okay, liquid solvent at the room temperature. So we are using, instead of the ammonia, we are using ethylene diamine. So in this condition, we can making of, okay, black. The surprisingly, which is the unexpected, we can making of the blue. So from the beginning, like, eventually we are looking for black at the room temperature, but when we apply with the P25, which is the mixed phase, and then we got the blue. So we're trying to figure out, but actually we are looking for black at the moment because the visible light, TiO2, we are looking for. Okay, so this is our conclusion. Okay, through our analysis, we found out mixed phase P25 giving a blue color, and anatase phase did not change. Rutile phase making a black. So this is one of the surprising result, which was not expected. So anyhow, okay, if you see that the visible light, the black one, as you expect, black one giving the largest absorption, and blue one giving the second one. So in the absorption, as we expected, black giving highest, and blue one is the second. Okay, so the conversion of the 12-month condition, and we found out our material have about 2-point-something electron volt, the band gap. So this is the example of the TEM. So this is the rutile phase, this is the anatase phase in the mixed phase, and then after treatment with our lithium EDA solution, and the anatase phase, okay, disordered only. And this is one of the strong evidence showing that this, from the XRD, this anatase phase, this is this is the anatase phase, this is the rutile phase. As the reaction goes by, rutile phase, TiO2 is the disordered, okay, disappeared. And also the selectively anatase phase did not change, but rutile phase completely gone. So which means that selectively we can remove disordered the rutile phase only. Okay. Anyhow, we trying to having a water splitting hydrogen evolution from the semiconducting material with the sunlight, right? So simply we mix with our black and blue TiO2 in the water with a solar simulator, and then we observing the gas chromatography, how much hydrogen gas is evolved. So this is the result showing that even though our blue TiO2 giving the best yield, so better than black, even though it's better than platinum. So through this result, we try to understanding why is blue is the best yield, better than black, much better than black. So this is our proposed. The proposed one is that So in the science paper, which was reported here, is that usually they making of the hydrogenation at the 200 Celsius degree. They can making of the black, the surface, okay, core shell making of the black here. So in our case, we have two different phase. Okay, this is the rutile phase, okay, black. This is the unchanged crystalline phase anatase. So what happened here is that, so observation of the visible light is, this is higher. But through the, after generating of the electron and holes, through the disordered phase, usually charge recombined. But in this case, in our blue case, the charge observing through the black with the visible light, and then nearby the crystalline phase anatase can charge separate. Okay, so through the PL, okay, measurement, we found out the blue one giving a very fastly, okay, dispersed. So the extron can away easily through the anatase phase. So that's the reason why giving the world best yield. Okay, so after we found out, our finding is that selectively only reduced one phase, which is the rutile phase, from the P25 mixed phase. So selectively disordered only one phase. And then the other one did not change the anatase phase, crystalline phase, can effectively charge separation, charge transport. This is our finding. So our next challenging is that, can we make the other way? Anatase phase change, rutile phase not changed. So which is the other way? So we're trying to figure it out through our analysis. So as you can see here, the rutile phase, crystalline structure, and anatase phase, crystalline structure. So as I mentioned about the two different phases, we found out anatase phase having an interlayer distance a little bit longer than the rutile phase. So our approach is that, as you can see here, from the alkali metal, the size, okay, the sodium and potassium is larger. So the second approach is that, if you changing of the size of the alkali metal, maybe this sodium, maybe this potassium will change anatase only, but not the rutile phase. Okay, so this has happened as you expecting. So in the sodium, anatase phase is changed, but not the rutile phase. In addition, also potassium. But it takes us so long. Okay, it takes about 3 years to have this achievement after first finding. So, okay, here is our conclusion. Right, through the Li EDA, giving a rutile phase changed, but the sodium, okay, EDA and potassium EDA giving a anatase phase changed. Okay, so until now, okay, through this basic finding, there are several companies trying to having a develop of this material, and then various application. now we technology transfer. The 3 company we did, and then another company is a big group. They are doing a technology transfer now. Okay, so through that, we making of one-phase rutile disorder and anatomy disorder after 3 years last year, and then we trying to figure out, are there something meaningful application? Okay, so this is the our another scheme by using our blue TiO2, and then the band gap position is about our blue TiO2 is like this. We trying to intensify the homo level here, oxidation part. Usually this is the reduction part, conduction band. This is the valence band. So when we did the water splitting, we use the sacrificial agent for the oxidation part. So our dream is completion. Without any the sacrificial agent, we're trying to intensify this part. So we are looking for one of the lowest material who having a homo level, the valence band. So we choose W3, which is one of the best material and also the cheaper one. So we are dreaming it having a the G scheme. If you have a G scheme, the charge separation from conduction and the valence band is much larger compared with the this type 2. Okay, so we're trying to figure out whether this is working or not. So we apply the CO2 reduction, which is the artificial photosynthesis. So in the CO2 with the water in our nature, by making of the this something meaningful chemical with the oxygen here. So through the CO2 reduction with the water system without any sacrificial agent, we're trying to having something meaningful product later on. But now we are aiming to have a 100% CO selectivity. Okay, so here is the something easily you understand. So we are using our blue TiO2, and also with the intensify here valence band using the W3 material by having this conduction band and the valence band having a large separation. We're trying to have a G scheme one, and also having the intensify of the conduction band, we adding a silver. So this silver can selectively making of CO versus CH4. Okay, so that is our scheme. So this is a synthesis with mixed together with the silver precursor, and we have this blue TiO2 W3 silver, and then we measuring of the CO2 from the CO and the CH4. So through the here the system this one can give only 100% CO selectivity, and also the performance one of the best in the world until now. And also, we're trying to figure out, okay, showing that our system is the G-schemed, not the type 2. If you have type 2, okay, here, if you have a G-scheme, okay, child separation here, right? So we try to have a G-scheme one. So to prove a concept here, okay, as you know that the valence band having a OH radicals, and this OH radical, if you're using this coumarin, if you generate of the OH radical, can give a 7-hydroxycoumarin, which is showing here. Okay, so as you can see here, blue TiO2 only not generating, but okay, with the WO3, okay, generating here, but in the mixed one, giving the best one. So which means that here is that, okay, hydroxy radical mainly making of this WO3, right? So through the, okay, this control experiment, and we found out our material, okay, pass through, okay, through the G-scheme. Okay, so this is the a real experiment to try to figure out this is really happened. So we're using a isotope water to trace this reaction. Also, we did it isotope of CO2 as a source of the CO product. So what happened here is that the reduction part, which is the conduction band, oxidation part in the at the valence band, and then okay, we start the material CO2 and water, right? And then through that, okay, in the oxygen part, making of the, okay, absorpting electrons, making of this intermediate, and the oxidation part, making of the, okay, these two protons, and also this hydroxy radical intermediate, isn't it? Okay, so if you can see here, starting here, 20 is this isotope water, and this one is the CO2, isn't it? Okay, as time goes by, 10 minutes, okay, 20 minutes, okay, 20 minutes here, and then, okay, 28 is increases, which means that this is the 12, 18 is 20, okay, this one is 12, 16 is 28, isn't it? Okay, and then as time goes by, okay, here, right, we found out there is the reaction, also with the reaction is completely reversible. Okay, so here is that this 2H plus from the water go to the reduction part, making of water again, and this water is go back again here. So without any sacrifice agent, only our material with the light can generate of continuously generate of the, okay, this CO and oxygen. Okay, so through this proof of concept, and then we found out we can do more something by using this CO2 reduction and trying to make our plan is by using this one, making of something meaningful product, like what our nature did. Okay, so through the, okay, our research in the P25 TiO2, which is the most effective fluorochemical material, we can selectively making rutile phase disordered only and anatase phase disordered only. we can control completely. So to remember, right, also the achievement, we put my name here, the Hyoyoung Lee's blue TiO2. So this is the first time, and then I think this is never, cannot break down, break up, because only the two phase we can selectively making one phase disorder and the other phase also disorder selectively. Okay, so here is some more the application. We try to having a photocatalytic nitrogen conversion to make ammonia, like the Prof reaction, but we are using the room temperature or a very low temperature, less than 100 Celsius degree, making of the production of the ammonia from our nitrogen. So this is one of our next goal. In addition, also, since we producing these two materials, we trying to recognize what is the charge transfer. How can we control the band modulation? Those things we are going to do. So if you are interested, please send the email to us. This is what I prepared today. I'd like to answer any questions. Thank you for your attention.
Thank you, Professor Lee. And now we are coming to the Q&A session. Now, we've already got some questions sent to the live platform. So I will pass this to Professor Lee. And as you mentioned, the creation of black titanium enhanced absorption over the whole UV visible range. So will you also cause the creation of defect levels? Because everyone knows that the defect levels will lead to the recombination of the electron holes or excitons. So with the increase of the light also leads to the decrease of the utilization of these exciton or electron or holes. So will this transform a lot of energy into heat? So that's the first question.
Okay, so actually that is true. People was looking for, as you mentioned, people are looking for black TiO2, like this. But eventually the efficiency of the black TiO2, right, this is not higher than blue TiO2, not higher than the white TiO2, because as you mentioned, the charge recombination happened. So in the commercial world, especially in Japanese people, right, selling many products with platinum, right, TiO2, white TiO2 with platinum, right, platinum, precious metals, gold, they are selling it, right, here, platinum, right, in the visible light one. So that's the reason why the charge transport is also very, very important. So even though we didn't know, I didn't know from the beginning, but through the result, I found out one part is the visible light absorption, but also the other place has to have a good charge separation. That is the main thing we found out until now. So only the black TiO2, even though higher absorption, but not better than just TiO2. So through that means that charge separation is also important, more important than absorption.
Okay. So the next question is the big one. So how do you think about the big future of the photocatalysis, especially for the TiO2 or something related? How far is it away from like something like the Nobel Prize? And as you mentioned, you have already got some industrial applications. So how is it like in the for example in South Korea? How is about the industrial application of this kind of materials?
Yeah, this is good question. Okay, in South Korea, it's about 15 years. People was very interested in it, but they okay, in our broadcasting, one of the SBS, right? They established in the tunnel in the subway, and then 15 years ago, they okay reporting the TiO2 was not effective. Then many companies was bankrupt at the moment, about 15 years ago in South Korea. But even though it's in South Korea bankrupt, but in Japanese, the company, Ishihara company or some other company, in German company, they still working on that. So they applying a precious metal, platinum. Okay, and okay, so through the in South Korea now, as you know, the coronavirus, isn't it? The COVID-19. So many company is pretty much okay trying to do developing visible light photocatalyst, because the as I mentioned about already, the hydroxy radical, right? This hydroxy radical can killing the bacteria, isn't it?
The virus, actually.
Yeah, virus or bacteria, right?
Yeah, yeah.
So yeah, okay, even though the hydroxy radical can break down the membrane of the bacteria, any kind of the virus, they can break down. But it's depending on the hydroxy radical, the amount of the hydroxy radical.
Yeah.
Isn't it? Yeah. So through the here, that's the reason why and also the inside, right? So now in Korea, our product, right, blue TiO2, now city company already did the technical transfer, and then now is the big company. But I cannot tell you. But okay, this is because it's going on. So we're trying to the company trying to okay, selling to the many other applications. So that is what the company doing now in Korea. In addition, also, why I put my name in here, the blue TiO2, Hyoyoung Lee's blue TiO2. I'm trying to, okay, really like to be one of the pioneer. Also, yeah, trying to be okay, differentiate what the people already did, and then okay, this is the okay. Also, I like to be one of the. I mean, if this is okay, spread out all over the world, I think maybe.
I think it's a good way, because like in organic chemistry, people used to use the NAM reactions. So probably in the future, the material scientists will try to do some NAM materials like they do.
Yes, yes. And also now, okay, there are okay, as you know, when we have a Nobel Prize season, usually the September and the November, there are many Japanese, you know, okay, guys are okay hearing the Nobel Prize in the photocatalyst. Okay. Yeah, so yeah, the Fukushima and Honda, they are reporting, as you know, that TiO2. Yeah. So I wanna be one of the men.
Okay.
Yeah, that's the reason why I put my name. Huh?
I believe you will be something.
Yeah. So okay. Why I'm expecting now is that here, TiO2, and the P25 here, and then this one. So nowadays, okay, 3 people, okay, having a Nobel Prize usually. So,
okay,
I'm expecting, because the thing is that, okay, has to be spread out all over the world.
Yeah.
Yeah, something benefit to our society, isn't it? Mankind.
Yeah, I agree. Yeah.
Yeah.
Okay. Due to the time limitation, so we are sorry to stop right here. So thank Professor Lee again for your exciting talk and answering of all these questions. Thank you again.
Okay, thank you. And also, please remember my email address here, hyoyoung@skku.edu. Okay,
yeah,
thank
so
you.
anyone interested, you can search the professor's name and you can get this, I think.
Okay, thank you.
Thank you.